We had some awesome ideas before the break about this data. We had two votes, quadratic, exponential, both of which curves. Now, how many of you ever heard of a quadratic before? Quadratic, it's pretty popular. Exponential, okay, fewer. The difference, I'd like to study both of them in this class. I want to study both of them in the class for sure because they both do show up in your lives quite a bit. I was called down a couple years ago to Ben PD. Captain, what the hell was his name? It was a sweetie. He was trying to put together some numbers to get more funding for his department. And he showed me the number of crimes and the number of misdemeanors and felonies and this, that, and this and that. And he had it all tied back to Ben's population. And he was trying to see if there was some kind of a predictability in the number of crimes, misdemeanors, felonies, whatever, as a function of the population or as a function of years that have gone past. So I took this data and just had a blast with just making scatter plots left and right all day long. One of my favorite models was an exponential growth model. How many of you guys have heard things like each year things grow 2%? Or each year things grow 3%. And certain things that were modeled, the United States population is fairly consistent, like 1.01% growth per year. Now that means that more people are being born each year because it's 1.01% of the previous year's number. So you're actually getting more people in each passing year, but it's a consistent percentage. That's the idea of exponential modeling. Exponential modeling is one such that each successive data point is a multiplier of the previous. So in other words, if you've got the one before it, you multiply that particular point by some constant number to get the next one. And this works great in a lot of contexts. Might work great for our data. I want to look at it. So I'm sorry, I'm using shorthands here. Each successive data point is a multiplier of the previous one. So in other words, if you know the data point before it, the y value before it, you're going to multiply that by some constant to get the next y value. Does that make sense? So I'll throw up an example. I won't literally throw it up. We'll put it on the board. So for exponential data, we'll have x's and y's here. So suppose, for example, let's just make the x's simple. 0, 1, 2, 3, just to make life easy for ourselves. 0, 1, 2, 3, 4. I'm going to get this podium out of the way.
Today we're going to talk about math.
So give me a starting point. Give me a starting y value. 12. I got 12. And the multiplier is usually given as some kind of a percentage. So suppose we go back to the one we used before, 1.1. So suppose the multiplier is 0.1, 10% growth each year. So to get the next one, if you have 10% growth, I'm making this up just to give you an example of exponential data. 10% growth, you take the 12, multiply it by 10%, which would be 1.2, add that to the 12, and that gives you your next data point. So it would be 13.2, wouldn't it? Which would be the same as multiplying 12 by 1.1. You get the exact same result. So the 13.2 would be this guy times 1.1. Your next data point, your next y value, would be 13.2 times 1.1, which would give you 13.2 plus 1.32, which I think would be 14.52. I'm doing my math right. I'm going to check me on that. But the idea of exponential data is you constantly multiply the previous. Oh, did I do it wrong?
No, I had a question.
Oh, question, please.
So you did the second number, 13.2, and you used 10% of that number, or 10%?
And add it to the previous one. So the reason this one's 13.2 is it's the previous one plus 10% of the previous one.
Oh.
which is the same thing as multiplying the previous one by 1.1. 110%, if you will. So this one down here would be the previous one, 13.2, plus 10% of the previous one, 13.2. Did I do that math right? Is it 14.52?
Yes, it
to do
is.
that?
Yes, it is.
Thank you. Check me on this, Tony, because I suck at arithmetic. The next one, whatever it would be 14.52, which is the entire other one, plus 10% of that 14.52. 15.972. Did I do that right? Check me on that. We're going to call it good. This is correct over here. I'm not sure if I'm adding it right in my head. But the idea is, and don't get too hung up on the mathematics, the idea is the next, got it? Thank you, Tony. Appreciate it, brother. The concern with exponential data, or the behavior of exponential data, is it makes sense to use it if you have some reason to believe that there is a constant multiplier at work. Now, I'll give you an example of when you use this kind of stuff. Does anybody have an aquarium or a pond in their yard, aquarium in their house, a pond in their yard? You guys, or even like a stock tank that you feed animals with. Do you guys have filters in those things? Filter the water? Right? Why do you have filters on your tanks and your aquariums and things like that? They clean it. You want to get rid of the bacteria, the ammonia, and things like that build up. There's good bacteria and bad bacteria. You want to get rid of things like ammonia and high phosphates because that can choke out fish or it can make your animals sick. So you put, say, carbon filters or biological media filters, sometimes just curl. If you ever run out of filter material, if you have the curlers from curling irons, throw those in there. They work great, plenty of surface area. The idea, though, is as the water passes over those media, whether it's carbon or curlers or whatever, you remove a set percentage with each passing hour. So, for example, after the first hour, you remove 70% of the bacteria, whatever's in there. After the next hour, you remove 70% more. After the next, you remove 70% more, and then 70% more, and then 70% more, which means you're removing less with each passing hour because there's less to remove, but it's the same constant percentage. That's one example. That would be exponential decay versus exponential growth. We'll get into this more frequently, or more in depth as we go into the class. Anybody ever take aspirin for a headache? What do you have to do after a certain period of time? Well, either number one, figure out why you get headaches, but you might have to take more. On Thursday, I was in my total fit class, and I went to do a drop kick at the ball, did a Charlie Brown, just totally laid myself out flat. It was a sheet of ice, feels sheet of ice. Laid it straight on my back, got a big old knot on my butt, and landed on my wrists. And I was like, well, that sucks. Took 4 aspirin. 6 hours later, took 4 more against the label's advice. But it was fine. This one went down, I iced it, I heated, I iced it, the whole rice thing. But the idea was, aspirin wears off after time. It's got what's called a half-life. It's got an amount of time after which half of the medicine is gone from your body. Why does the medicine go away from your body? Because you have a liver, and that's the liver's job. It tastes that and said, get that the hell out of here. I don't want that in my body. That's the whole point of the liver. That's why it gets worked out on Friday nights sometimes. So the idea is certain types of filtration. Your liver is basically a filter for your body, like your filter is a filter for your pond. So exponential models make sense when you have a multiplier that's at work. So that's a question right now. I'm not sure if we do have a multiplier at work. Let's come back to that, okay? Let's come back to see if we can convince ourselves there's a multiplier at work. So let's talk about quadratic, because I think most of you have talked about quadratic. So here's exponential. Here's quadratic. Some of you have heard about quadratics before. Tell me about quadratic models or quadratic equations. Tell me anything you remember about quadratics.